Categorical variables describe membership in distinct groups, but quantitative variables operate on an entirely different scale. Measurements such as height, blood pressure, cholesterol level, income, or reaction time can take on a wide range of numerical values along a continuum. When presented as a raw list, these numbers are often difficult to interpret on their own. To extract meaning from quantitative data, we must organize and summarize it in a systematic way. One of the most effective approaches is to group numerical values into intervals and display the results in tables. These tables provide a structured summary of the data and serve as the foundation for graphical displays such as histograms, stem and leaf plots, and dot plots. Well-constructed tables help reveal key features of a distribution. They show where values tend to cluster, how widely the data are spread, and how observations accumulate across the range of possible values. By organizing quantitative data before visualizing it, we gain insight into its overall shape and structure that raw numbers alone rarely provide. A frequency distribution for quantitative data is a table that organizes numerical values into a set of non-overlapping intervals, called classes, and records how many observations fall into each class. Instead of examining individual data points one by one, a frequency distribution provides a structured summary that reveals the overall pattern of the data. Each class is defined by a lower limit and an upper limit, and together the classes cover the entire range of the data set. The class width is the distance between consecutive class boundaries or lower limits, and the range of the data is the difference between the maximum and minimum observed values. Thoughtful choices about the number of classes and their widths are essential. Too few classes hide important structure, while too many classes make the table overly detailed and difficult to interpret. The purpose of a frequency distribution is not to preserve every detail, but to highlight the shape, center, and spread of the data in a compact and interpretable form. Steps for constructing a frequency distribution. Step 1. Decide on the number of classes. A common guideline is to use between 5 and 20 classes. Fewer classes may oversimplify the distribution, masking important features such as skewness or multiple peaks. Too many classes, on the other hand, can make the distribution appear noisy and obscure the overall pattern. Step 2. Compute the class width. Subtract the minimum value from the maximum value to obtain the range. Divide this range by the chosen number of classes, then round up to a convenient number. Rounding up ensures that all observations fit neatly into the defined classes without overlap. Step 3. Determine class limits. Choose a starting point at or slightly below the minimum value, then add the class width repeatedly to establish the remaining class boundaries. Consistent class widths make the table easier to read and interpret. Step 4. Tally the frequencies. Count the number of observations falling into each class. Each observation should belong to exactly one class. Suppose a dental researcher records the number of cavities filled for 40 patients in a clinic over the past month. We want to summarize the distribution of cavities per patient. Because the data are counts, classes of width 1 are natural and easy to interpret. Each class corresponds to an exact number of cavities, 0, 1, 2, 3, and so on. The frequency distribution shows how common each count is and immediately reveals whether most patients have few cavities or whether higher counts are common. Now consider a study measuring systolic blood pressure for 60 adults. Unlike cavity counts, blood pressure is a continuous variable, so it makes sense to group values into wider intervals. The minimum measurement is 86.8, and the max is 153.6, which gives us a range of 66.8. If we choose 7 classes, then we find the class width to be 66.8 divided by 7, which equals about 9.54. We will round up to 10. We use 85 as the starting point since it is slightly below the minimum measurement. Now we can construct the intervals and find the frequencies for each. Here the classes span 10 millimeters of mercury intervals, such as 85 to 95, 95 to 105, etc. This grouping smooths out small measurement differences and highlights the overall distribution where most values cluster, how spread out the measurements are, and whether unusually high or low values appear. Raw counts are helpful, but sometimes we want to know what proportion of observations fall into each class. The relative frequency of a class is the class frequency divided by the total number of observations. If you add successive relative frequencies as you move across the classes, you get the cumulative frequency, which tells you the proportion of observations less than or equal to a given class boundary. Each entry is the sum of the current class's relative frequency and all those below it. Because it represents a running total of proportions, the cumulative frequency increases monotonically and must end at 1 or 100% in the final class, reflecting that all observations have been accounted for. A graphical display of cumulative frequencies is called an ogive. An ogive plots the cumulative proportion, or cumulative percentage, on the vertical axis against the class boundaries on the horizontal axis. Each point on the ogive shows the proportion of observations that are less than or equal to a given value. We can extend our cavities example to compute relative and cumulative frequencies. Selecting an appropriate number of classes is more art than science, but a few guidelines help. Many textbooks suggest between 5 and 20 classes. An alternative rule of thumb for histograms is to use 5 to 15 bars. As the sample size grows, more classes allow finer detail, but too many classes produce a sparse table. In practice, try several class widths and see which one provides a clear picture of the data. Software like Jump and R will automatically suggest class widths, but you can adjust them manually.